for joining us, and welcome to today's session on data-driven perspectives on threat trends. My name is Ryan Holland. I'm from the Amazon GuardDuty team, and I lead security and security engineering. And I'm joined by Paul.
Hey, nice to meet you. I lead the Shield threat research team, which is focusing on analyzing our inbound threats and turning that into actionable intelligence. Yeah, I got it. Ryan, thank you. Ryan will be back up on stage a bit later. Thank you so much for joining us today. We're excited. It's a Thursday afternoon after a long week, and I'm sure there's some fatigue here. I really appreciate you coming here and supporting the talk, and we hope that you get something out of it. This is a 200-level talk, so we're going to look at some high-level trends, try and understand what we're seeing from a GuardDuty perspective and from the perimeter of the AWS network. And there's no doubt going to be some slides in here that are a little bit technical as well, so on average it's a 200-level talk. And I hope you enjoy that. What we're going to cover is how we approach threat research, the types of systems that we've built to analyze and find trends, and then talk through how our defenses on our network are designed to use this intelligence and protect the availability. And then again, from GuardDuty, who's kind of like sitting on the inside of our network looking out, what they're seeing from their perspective. So starting off, our goal, at least my team's goal at Amazon in our perimeter protection organization, is to, this is our mission, right? We want to make AWS an unattractive target. We recognize that you can't eradicate threats, but the more work we do to make it difficult to target us, and more expensive for bad actors to target us means that AWS becomes an unattractive target, which means it's safer for anybody running workloads on top of AWS. And what we do is we have built systems that analyze inbound traffic and look at sort of the heuristics of what we're seeing there, looking for anomalies. And once we find that, we have systems that automatically work backwards from those anomalies to figure out like what data or what indicators in there is interesting, and we use that to build features and protect our customers. The last point here is important. We're going to touch a lot on this in the talk. There's a distinction between mitigating attacks and disrupting. Mitigating is placing a filter, a rule that is dropping traffic that you don't want. Disrupting is efforts that we do to prevent bad actors from easily just re-attacking us. And that involves taking down infrastructure and kind of trying to really get deep and go beyond our network to figure out who is attacking us. So we're going to talk more about that. To start off, this is the scale that we work at. Our team is situated on top of this network, right? It's one team looking across this massive scaled network, looking at thousands of DDoS attacks every day, tons of web traffic that goes through our AWS managed rules. And all of this is a data point and a source for us. On the DDoS side, it's not going anywhere. Actually, we've seen close to 1 million DDoS events detected and mitigated this year, which actually over the last 5 years is pretty consistent. However, for the first time this year, application layer events are the majority of what we see. For previous years, since DDoS started, network layer infrastructure events were the majority. Those are like SYN floods, UDP reflection attacks. Those kinds of attacks that are on the lower network layers are what we would typically see, and that's well understood today and easily mitigated. But where all the innovation is on the application side. This is the innovation on the bad actor side, which is also forcing us to innovate. 40% year-over-year growth, and finally, the application layer has taken over, and this year to date, we're sitting at 56% of all DDoS events involving application layer. There are many reasons for this. Our team has worked backwards and tried to figure out motivations for DDoS, and there are numerous reasons. It could be some script kiddie writing and trying to take down a gaming server who eventually realizes how fun that is and then ends up years later targeting critical infrastructure. depending on the resourcing and funding that they've got. But all of this allows us to figure out different tactics and techniques that they're using to DDoS us. One of the biggest trends we've seen is in the use of proxies, right? A proxy is a server that's on the internet. When you send it a request, it will forward on that request to the destination that you've specified. So if you're a target, if you are the target in this diagram, and you receive requests from a proxy, you don't know where those requests originally came from, right? Because the proxy is hiding the original source. And there are thousands of proxies on the internet. Most of them, according to our knowledge, are just open proxies. That means they're not authentic. You don't need authentication to use it. Anybody can do it. If you're a student and you're trying to get off your student network because you want to browse something that you're not allowed to, this is a great way to do that. You use an open proxy. So there's legitimate traffic going through these proxies, and they're a great way for bad actors to obfuscate their compute capacity that's creating these DDoS attacks. Those we refer to as proxy drivers. And so our goal is trying to figure out how do we figure out where this traffic is coming from? How do we understand where those proxy drivers are situated? This attack is, this use of open proxies is very different to a botnet. So I've got this picture here just explaining how a botnet works, right? A botnet is, in the bots section there, is compromised infrastructure, right? So if you leave an instance open on the internet, unsecured, running vulnerable, unpatched software, there's a chance that a vulnerability will be exploited, and it will install some malware or some software program on your instance, and that then becomes part of the botnet, and these bots are then controlled by a command and control server, kind of like the brain of the network. So this is another thing we see, but more often, you can do application layer attacks with this, but more often than not, we're seeing these proxy-based infrastructures attacking us at the application layer. So one of the interesting things we do is we track DDoS infrastructure. No doubt you've probably tried this. If you think about your application architecture, you probably keep track of the IPs that are causing pain for you, right? The IPs that you don't want. You maybe got a block list with IPs that you know about. And we do this, except we're doing this across the entire AWS network. So we're looking at all the known offenders, particularly in this application layer space, that are contributing to DDoS attacks. So in a simple example here, you've got two clients, sources contributing to 3 different DDoS attacks. And so we take these ones that are the most prevalent offenders in this space, and we keep track of them. And they become on our bad list. And this has proven to be unexpectedly very effective. And I think that's because we're doing this across our entire network. So actually, from the millions of DDoS attacks we see in a year, 56% of those are application layer attacks. So we've got like more than 500,000 attacks. We're tracking around 30,000 individual sources that are constantly hitting us, right? And I think the takeaway here is that most bad actors don't have the funds just to find new infrastructure and find new IPs. And so surprisingly to us, this has been a successful tactic just to quickly place a mitigation using this list. And if bad actors are listening to this and they now go change their IPs, that's okay. We'll catch you. This list actually is available to you. It's super helpful for us protecting the availability of infrastructure, but it's also in a managed rule group in WAF. So if you use WAF on your ALB or your CloudFront distribution or API gateway, the list is in the AWS managed IP reputation list, and it's there for you to use. There are some other rules in there, but the one that's called the IP DDoS list is the one that has this exact intelligence that we've collected from across our network. So please use that for yourself. That's available for your use. Just to give you an idea of how we've used this. We use this list to protect our management console. We've deployed this list across all our CloudFront distributions. And in all of these situations, we're rate limiting and just impacting the ability for large volumes of requests from these known offenders that we know are bad, hitting your endpoints. And a lot of what we see from there is proxy-based attacks, right? So immediately, your endpoints and your applications are protected from that. An example of how we use this for the retail store, we had this list deployed during the Prime Big Deals Day. And in October, I think it was, 2 days, we had 12 DDoS attacks. And all of those attacks were mitigated with 92% efficacy with just this list, right? So remember, like, DDoS defense is a multi-layered approach. This is just one layer that we place, and for free, essentially, you get 92% efficacy. And so I really encourage you to use that list. If you're using Shield Advanced has a feature called Layer 7 Auto Mitigation. And this feature places the list for you as one of the things it does automatically. So if it detects an anomaly based on the deviation from your baseline traffic, it will place this list, and your list, your application is then immediately protected with this IP list in there. Now, IPs are a great first quick mitigation, especially when you know that the list is a list full of bad offenders who are repeatedly attacking. But again, we also analyze the traffic and deploy an HTTP signature that kind of captures the attack traffic. So that allows us to have 2 layers of mitigation automatically in your WAF web ACL. Now, an area that I am very passionate about, and something that we've only just recently spoken about in the public space, is something that we call Madpot. This is how we collect global threat intelligence on the AWS cloud. It's a sophisticated system that we use that has sensors or honeypots that we use for monitoring and detecting and understanding the noise that's out there on the internet. It's an integral part of how we collect this intelligence because it allows us to see what your applications are exposed to every day, right? Anybody can create a honeypot. It's not that difficult. You create an EC2 instance, and you just leave it open to the world. You'll see what happens. You'll get a lot of traffic. So it's helpful to us because we run on these honeypots applications, and we respond in a way that mimics vulnerable applications with unpatched versions. And that allows us to potentially pick up what bad actors are doing to these types of instances out there. So just to give you a bit more detail about Madpot, we have more than 10,000 sensors deployed globally around our network. And every day, we're getting more than 100 million potential threat interactions. So an interaction is somebody who finds a honeypot and interacts, like sends it a payload or a packet and tries to do something on that honeypot. And out of this, every day we're able to classify around 500,000 malicious attempts to interact with our honeypots. This is crazy. We're collecting all this data, and it's allowing us to have this unique global perspective of the threat landscape, of the internet, the noise, the bad noise that's on the internet that you have to face day to day. And so it gives us insight into the trends and allows us to learn a couple interesting facts about the threat landscape. For example, 3 minutes is all you have. Now, what I mean by this is when we deploy, or on average, when we deploy a new sensor that's got a new IP and it's out there on the internet for the first time, you have roughly 3 minutes before somebody tries to exploit that instance. 3 minutes. It's crazy. And that's on average. And I know we're all here in Vegas feeling lucky. And if this does happen to you and it only takes them 3 minutes to find you, then you struck the jackpot. Because a lot of what we see actually happens quite quickly and in under a minute. Remember, this is an average across a massive data set. So it's, I guess you're lucky if you only hit 3 minutes. But what this does, and I'm not trying to create fear here, but I do think that this data helps us reinforce the idea that we have to raise the bar in the systems that we design. We have to think about the way that our systems are analyzing the logs that we've got and trying to figure out if something bad has happened or if something has been compromised. I don't think that a weekly or daily scan of your logs and infrastructure is enough, is what the slide is saying. So I wanted to share that data point with you because I think it's important for us. We use this data from Madpot to raise the bar of our internal security systems. And it's good for you to understand that you can't just sit on your hands because there is all of this out there. So Madpot's not just a honeypot system, right? It's not just like the value that we get is not just by running a honeypot. Anybody can do that. As I said, you can build your own thing on EC2. The real goal here is how we extract threat indicators and threat data and insights from the interactions. And so Madpot is integrated into our network. Now, we are extracting data on the exploit attempts and figuring out, hey, these are signatures that are now commonly being used by bad actors. And we're figuring out these are the types of malware that they're using, new versions of malware that we are able to download. We're able to reverse engineer. We're able to detonate and collect insights from the network activity. This kind of gear, this mechanism is powering a lot of what you see and what you are benefiting from in GuardDuty, in WAF, in Shield. And these are our external services. Internally, we use this to raise the bar of our own security posture of our network. And this allows us to hold on to that commitment of ours that security is job zero. Since its rollout, this technology has become a constant part of our cybersecurity strategy. And we've been running this for years, but recently have only just been speaking about it in the news. So there was this article that came out in October. AWS stirs the Madpot busting bot baddies. And Mark Ryland is one of our execs here. He's been helping us work through this. Has done a great job in allowing the public to know about the security controls that we've built. Just some examples here. So in May this year, there was a nation-state group a hacking group that's called Volt Typhoon that allegedly planted malware and spyware across US critical infrastructure. And by using Madpot, we were able to learn about their tactics. We were able to identify some information on them and work backwards from that to figure out customers that may have been in the crosshairs of this group. And we alerted, the article talks about this, but we alerted those customers and we were able to work with them, as well as providing this data to federal agencies that who are able to go above and beyond what AWS is entitled to do. Similarly, there was another group called Sandworm. Sandworm is a group tied to Russia, and they tried to exploit what they thought was a security compliance on our network, which turned out to actually be one of our honeypots. And so just from that interaction, we captured IP addresses and signatures of their attack techniques. And by taking a step back and looking across our AWS network, we could identify, again, customers who were in the crosshairs, and we could reach out and enable them to improve their defenses. So these are just two examples of how we've been able to use this insight and to protect AWS customers. Now, a big part of what we do is we use this data to work and cooperate with outside internet players. So what this action looks like is what we refer to as a takedown. When we identify that there are botnets or C2s or proxies or proxy drivers out there, any type of infrastructure that is continuously causing harm, we will reach out and say, here's all the information, please will you take this down, right? This is our effort to cleaning up the internet, right? Because we're learning about this infrastructure from Madpot, and we're asking them to remove it from the internet, which means that everybody on the internet has a better time. Ultimately, you might think, okay, but they're just going to rebuild it. Sure, they will. They will rebuild it. But this is us driving up the cost. This is us disrupting them. If we don't do this, then they can just re-execute that 50 lines of Python and initiate an attack. By disrupting them, they've got to go and build things. For example, a botnet typically has some redundancy built into it, right? If you think about those C2s, the C2s are the brain of the network. And the C2s, if you take out a C2, the whole network dies because you can't control it. So what bad actors do is they have a domain name that resolves to many C2s. And so by taking down the domain and having the domain registrar deregister that domain, you now have to go and re-update all your bots, your whole network, to point to a different domain, right? And that's time, that's money, that's downtime for their DDoS as a service, so it costs them that loss of revenue. And all of this means that when bad actors know that AWS is doing this, then they hopefully are going to think twice about targeting anybody on our network. And that's our goal, as I mentioned in the beginning. So a way that we get intelligence on the proxies is by this. We run these honeypots that pretend to be proxies. Right? They're not actually forwarding on any traffic. They're just responding as if they were a proxy. And so by having this here, our proxy honeypots end up on lists that are out there on the internet. They end up in tools that are used, free tools that are abused by people to execute DDoS attacks. And that's great. We're not making the world a worse place because we're not forwarding on the traffic, but we have all the benefits of getting the insight into the compute capacity on the proxy drivers. And so we can then initiate takedown requests for proxy drivers. Here is just some information on these are basically our partners, right? These are networks out there on the internet where we are tracking proxy drivers. And by kind of handing over the details to them, we're achieving two things, or three things actually. We're cleaning up the internet, right? Anybody on the internet is benefiting from us because we're taking down malicious infrastructure that's not just targeting AWS, but everywhere. The second benefit is that these networks are saving money because their resources, these resources and these accounts that are being used by bad actors are causing costs, and they're able to clean up their own backyard and take action based on the data we provide them. And then thirdly, they're able to build mechanisms, right? By educating them on this is the type of traffic, this is how you find these things, they're able to build mechanisms that allow them to detect this in their own way. So we're empowering them to clean up their backyard even in a more efficient and effective way. So we work with these guys to achieve that. Here's some examples. So here's one example. I think this was DigitalOcean we worked with, and they responded to us saying, hey, we terminated one user. Not quite sure what that means. All I know is that they took some action, which is great. They terminated something, and that's excellent. This is what we want to see, right? We told them about some data, and they went off and did it for us. Here's another example where we shared some information on them, a bunch of IP addresses, and they were behind open proxies, so these were the proxy drivers. And again, we got some response here saying, thanks for sharing that, we've wiped these accounts. This is happening day in and day out. We're partnering with these accounts to do that. And I think that if there's one way that we can combat this type of malicious activity on the internet is through this collaboration between what we're learning and kind of these wider networks. Now, for my favorite thing, this is this is a sensitized version of what we found on a Telegram channel. It was a win for us when we saw this. This was some bad guy complaining about how good Amazon is at tracking botnets, tracking open proxies, and now we're even tracking spoof traffic, which is true. So the more I see of this, the more I know that our team is doing a great job of creating mechanisms that are resulting in AWS being an unattractive target. And so I take pride in the fact that we're able to achieve this mission, and for years to come, we're going to be continuing this mission to make AWS an unattractive target, because as I said, I think by doing this, any workload that's running on our network is safer. So I'm now going to hand over to Ryan. He's going to talk about this other perspective from the GuardDuty.
Thank you very much. For those of you not familiar with GuardDuty, GuardDuty is a threat detection service that customers can enable on their accounts. And we're looking for compromised users, compromised instances, any indication that something within the customer's account has suffered some sort of a compromise, whether it be at the application layer or if it's something with the credential. And we have a pretty wide visibility as well. So we're used by about 90% of the top 2,000 customers. We help protect millions of different AWS accounts. And in average, any moment, we have over 500 million running EC2 instances that we're helping to protect, and millions of S3 buckets as well. So it gives us a pretty good set of visibility, and we look at multiple different log sources. So when we first launched GuardDuty 6 years ago at reInvent, we were looking at EC2 flow logs, DNS logs, and CloudTrail logs. So that gave us a perspective of the network activity of the instances, as well as the user's interaction with our control plane through CloudTrail. And those first two are really what we're going to look at deeper here today as it applies to looking at the trends with the compromised infrastructure, as well as some of the other ones like EKS audit logs. After we did the initial launch, we got requests from customers to kind of expand the aperture and look at other log sources. So we added data events for S3 so we can understand how users were interacting with S3 at the data plane. And then as we saw more and more customers moving into containerized workloads, we saw that as an area that needed to get some good threat detection. So we started inspecting EKS audit logs, and that's the audit logs to the EKS of the Kubernetes control plane itself. And then this year, we added 3 additional data sources. So the first one was looking for anomalous behavior in Aurora, RDS Aurora login events. We added Lambda flow log events, and we'll look at some examples of why here later on. And then earlier in March, we added EKS runtime protection that gave us deeper visibility into what was actually happening at a process layer from getting kernel events. And then this week, we also extended that to include ECS, as well as Fargate and EC2 as well. So now we have visibility across all the possible compute platforms within AWS. And when we get these logs, we apply threat intelligence. And we look at threat intelligence in several different ways. So we partner with some third parties for feeds. We generate some of our own, and we get a lot of great threat intelligence from the Madpot team as well. We also employ machine learning to help identify anomalous behavior within your individual account, either at your account level or at the user level within your account. When we start looking at things like EKS, we're looking for different behavior or anomalous behavior for the cluster level. And then we also have the ability to do malware detection as well. So when we notice a signal, we notice something from an instance, for example, that is behaving in a way that is consistent with a malware infection, customers can enable the ability for us to snapshot that volume, run a malware scan, and then capture the malware that's sitting on that instance and help the customer find where that infection is. We have 164 different finding types. Obviously, we'll only look at a few of them here today. But customers can consume these through multiple different ways. So we have a console, obviously, but also we send them out EventBridge, which is probably the most common way to consume those. That allows you to make automated response. So you can trigger a Lambda function. You can send it to some of our partner tools. And you can also investigate those using Amazon Detective as well. So as I mentioned, we want to look at a few examples of the data that we're seeing from our vast viewpoint of our customers of what is the activity that we're seeing when their workloads are compromised based on the types of findings that we're generating for them. So by and large, the most prevalent action that we see when an instance gets compromised is crypto mining. So it's important to note here too, because when you start looking at these percentages, a lot of times we don't just see one single thing. So crypto mining is the most prevalent, but a lot of times we'll see the same threat actor use multiple different tactics. So they might have it doing crypto mining while it's still sitting there waiting for commands to do denial of service when the C2 is ready for that. Some cases also, depending on how it was compromised, we might see one threat actor go and start doing crypto mining, and another one will make it part of a botnet to do DDoS later or do something else. So it's not only just crypto mining. But this is our most commonly seen post-compromised activity. And it's actually almost very useful. This is a very good and easy to detect signal when crypto mining takes place. Some of the data that we look at too to help enrich our ability to detect this is what are the ports these crypto miners are running on? So when you're running a crypto miner, it's communicating to a mining pool. So that way the adversary can get access to the crypto coins that it's mining using your infrastructure. The most prevalent one we see is Monero. So XMRig is very, very popular. And we see very strong data around the types of ports that they're using. So 3333, 2222. They use a lot of ports that are pretty easy to remember, but also don't generally have other well-known or typically good purposes. One of the other things that we see is where are these mining pools running? And to be fair, it's nothing wrong with running a mining pool. It's perfectly legitimate as long as you also are paying for and own the infrastructure that's doing the mining, which isn't the case here. But we see also a pretty strong concentration of the ISPs where the crypto pools are located. And this gives us some good signal too. So we have our threat intelligence, we have some machine learning that can help us identify patterns of behavior that look and appear to be crypto mining. But if we see activity in flow logs that is on some of these well-known ports going to some of these well-known ISPs, it can also help be a signal for us if we don't already know about that mining pool, because they're pretty easy to move around and then the bad guys will set up new ones. We can then go and automate a system to probe that, test if it is an actual mining pool, and then update our threat intelligence and make the better detections going forward. From a customer perspective, if you have GuardDuty on and you start to do crypto mining, there's a whole set of different findings that you're going to start to get from us, right? That'll give you signal that your instance is compromised and that you're now performing crypto mining. And we get them from multiple different sources depending on how the crypto miner was configured and how they were communicating with the mining pool. So flow logs, which is connection events. So you're looking at the source IP, the source port, destination IP, destination port, and protocol. If the IP address of the remote side is a known crypto mining pool, we'll give you a cryptocurrency finding from flow logs. That network port unusual, again, very useful for us getting that signal around, hey, we actually didn't know about maybe this particular mining pool IP, but we're seeing that this instance, and the way this finding works is we track for every instance and every group of instances, what are the typical ports that you make outbound connections on, so that you actually initiate an outbound connection, and what are the ISPs that you typically communicate with. So if all of a sudden an instance is never communicated outbound on port 3333 and it's going to one of those ISPs that we just looked at, it's a pretty good signal that it's probably a mining pool. And so that's another good signal for this. Depending on how the mining pool was defined, it might use a DNS name instead of an IP. They'll do this often because, again, IPs are really easy to change, they're really easy to take down. So they'll use a DNS host name, and then that way it can resolve to get whatever the most current IP is. So from a DNS log perspective, we can get a Bitcoin tool finding based on the domain names being queried. And the one below that is another one of our machine learning algorithms where we look at the DNS requests across every AWS customer globally, and every day we build a reputational graph based on all of that data. And it allows us to predict potentially malicious and also known benign domains. And so we feed that back into our threat intelligence, and we have a category for that where we're saying, based on some of the activity that we're seeing, we believe that there's a likelihood that this is a crypto domain, even if it's not presently on known threat lists. And what we tend to see is we're finding a lot of malicious domains, both cryptocurrency and other types of bad domains, days to weeks before they end up on known threat lists. For customers that are using the runtime protection, so on for either EKS or ECS and Fargate and now EC2, you'll get all that same information, but instead of just getting the IP and the domain, we'll also be able to give you a lot of really rich context about the process itself. So the process ID, the path to the miner, who launched it, what its full process lineage was. So that really helps with the investigation because now you know exactly where to go. And then lastly, like I said, we have these for Lambda as well. And this was really in response to, we started seeing in some cases where accounts had been compromised in order to hide the crypto mining activity rather than spinning up new instances, right? Some of the adversaries started to realize that customers would start to notice if all of a sudden you launched 400 large instances in their account to do crypto mining, so they would try to hide it in Lambda. So now we will also process and analyze flow logs coming out of Lambda functions and can identify crypto mining there as well. So we did a real world test in one of our environments just to see kind of to that point of time matters, like what happens if we exposed something? So we took an EKS cluster, configured it, and we made a misconfiguration. And unfortunately, this is a misconfiguration that we see happen in real life on real customer environments. And that is to allow anonymous access. So in EKS and Kubernetes, you can bind the system unauthenticated or system anonymous user to a cluster role. And that means anyone can use that API without providing any authentication. So that happens at T0. 9 minutes later, we saw that that was being probed by just generic internet scanners. So just a generic scanner came by and identified that. It was probed. And then 45 minutes after that, we saw very specific probing. So actually querying some of the specific Kubernetes APIs to see what it could do essentially on that exposed host. So sometimes people will bind an anonymous role to some less important APIs. In this case, we kind of gave them everything. And then 4 days later, we saw them actually start to use this information. So clearly, these were automated scanners. They're collecting information out there. And then 4 days later, we actually saw the first privileged action that started taking place. So they started using the secrets API in Kubernetes to retrieve some secrets off the host. They did a privilege escalation by launching a privilege container on the host, and then started launching new pods that were using repos that had crypto miners in them to perform crypto mining. And that all happened about 10 hours after they started doing the privileged actions. From this type of activity, we generated for ourselves, and we did this, a whole bevy of findings that actually kind of walk you through an entire attack chain. So that initial misconfiguration generated a finding for us saying, you have made this mistake, right? You have exposed your Kubernetes cluster in such a way that anonymous access has been granted. When that first Kubernetes-specific scanner comes along and it starts probing those APIs, like I said, that generally start off doing some Git operations just to see what it is they can do, we start generating discovery findings. So we're kind of walking through the attack chain here. When they started requesting secrets, now that's more of an impactful one, so you'll get a credentialed access. So this was a successful anonymous access to credentials. And then privilege escalation when we saw the creation of the privilege pod. And then lastly, the impact was the creation of new workloads, so the new pods that were being added by an anonymous user. And then with the runtime agent, of course, as soon as the crypto miner was started, we had a finding that there was an executable that was launched that was a known crypto miner, followed by the DNS request to the mining pool, followed by the IP traffic as the miner began to communicate with the mining pool. The second most prevalent action we see is using the instances as a launchpad for spreading further intrusions. So we see this in about 50% of the workloads that we see. And again, a lot of times this is in concert with crypto mining. And this happens because a lot of times the way the adversary gets in is through some sort of an application vulnerability. And so what we'll see is they start looking for other IPs on the internet that have the same vulnerability so it can attack them and spread. And so we see things that we call port sweeps. So a port sweep would be where I'm picking a very specific port. So I'm looking for a PostgreSQL database, but I'm going to go look for PostgreSQL databases across a very large number of IPs. We also see port scans. So a lot of times this is more looking for lateral movement, where they'll start scanning all the IPs inside the VPC to understand what other infrastructure is running in there, understand what ports those have open, so they can figure out if there's a way where they can find lateral movement onto other hosts, usually with the hope of increasing their privilege level. And then outbound attacks for brute force are very common as well. So the ports that we see for port sweeps, so this is some data around when we see these infections, and this changes over time, usually in relation to what is the more common or recent application vulnerability that we're seeing adversaries start to target. So when we got this data, Postgres was very prevalent. We almost always see a lot of outbound SSH, so people are constantly trying to use compromised infrastructure to run brute force attacks against SSH instances that are accepting traffic from the internet. And then the Windows management interface, so WMI, we see a lot of those too for brute force attacks. A lot of times either brute force attacks, but also looking for unpatched Windows servers as well to use some older vulnerabilities. And then the other ones that we see on there is interesting is like 8088, which is often used as a proxy port. So again, looking to find open proxies that they can know about and then start using. For these, we have a whole set of findings that we get from this data from, and that is, again, like port sweep, like I mentioned, where we're looking for a whole lot of IP addresses that a single instance is communicating with. And we look at and understand what is the response rate. So it's one thing to go talk to a lot of IPs, but if I'm talking to a very large number of IPs on the same port, and a very small percentage of them are answering, it's a good chance I'm just shooting blind across the internet, and I'm not actually purposely trying to connect to my or a known server in that case. And then outbound brute force for SSH and also for RDP. Very good reasons to keep your security groups tight and not leave these on the internet. They are constantly under attack, both from compromised infrastructure in AWS, but also from the wider internet. And then, like I mentioned, the Windows management interface brute force as well. Denial of service bots, we also see these as well, and around 20% of the attacks that we see. And it's important to note too, so when we see the denial of service, we're looking at the traffic flows. And again, we're gauging what is the number of packets out versus packet in, what's the response ratio, how many resets are we seeing? It helps us identify likely outbound denial of service. So this is very different than Shield, which is looking for protecting our customers from denial of service. This is more where your infrastructure has been compromised, you've been added as part of a botnet, and now they're using that infrastructure to try to send these attacks. One thing that we also do, just from an AWS-wide perspective, is when we find those C2s, we can null route them. That tries to break this chain as well. So even if your instance does try to communicate to that C2, it oftentimes will fail, because if it's a C2 we know about, we've null routed it, and they won't be able to communicate. The finding types that we have for this are very simple, denial of service, and we break it down by what type of port or protocol, what kind of protocol was used. So DNS-based, TCP-based, UDP on DNS ports, or just unusual protocols in general. One of the last kind of trends that we tend to see, and we're seeing a lot more of actually, is as we start to add more and more detective capabilities, adversaries start to learn what's going to get them caught. And like if I'm deploying some sort of a payload that has a miner on there, for example, I need to communicate to a mining pool. So I want to use a well-known one. It's going to have a lot of IPs that'll change over time. Having my first stage include a DNS name is very convenient. That means as the IPs change, the DNS will just pick up new ones. I don't have to update my payload. Well, these guys have gotten a little wise, and they realize that customers, and even with GuardDuty, we're looking at these DNS requests, and we're monitoring those to understand whether or not the DNS is going to a no malicious domain. So they'll try to evade that by not using the pre-configured DNS name. So when you configure your VPC, you define your DHCP option set, you tell all of your instances what DNS server you're going to use. Most often, that's going to be the VPC-provided DNS. Customers also can use their own as well, which is perfectly fine. And when they're using their own, they'll probably have something that's looking at those logs too. So they realize that GuardDuty is now watching all of these DNS requests and can flag this activity. So in order to avoid that, what you'll usually see on the first stage that's downloading the next stage is they'll override the connection by saying to the operating system, use this very specific, publicly well-known, commonly used public DNS server. And then When that happens, of course, there's no log in Route 53 for us to see because the DNS request went to another DNS server. What we're also seeing increasingly, too, is more sophisticated ones starting to use DNS over HTTP and DNS over TLS as well. So in the latter, and even encrypting those requests over TLS. So in response to that, we created some new findings to help detect this. And these work by profiling the DNS behavior within an account. So it's perfectly legitimate to use any DNS server that you'd like, and so that's fine. What we do is we look at your account, we look at your instances, and we understand, do you normally always use our VPC-provided DNS? Or do you normally always use a particular IP address that's associated with your Windows Active Directory server, for example? And over time, we learn about that, and then if all of a sudden we see you making a request to a known DOH server or a publicly known DNS server that's not one that we see typically used in your account, it's unusual. It's probably not what's configured within the infrastructure, and thus it's an override at the operating system level, and likely someone trying to evade detection by doing so. And that's our talk for today. I want to thank everyone for coming, and I do hope that you do complete the survey, please, for us. Thanks.